Ground rods offer enhanced grounding by providing a direct and low-resistance path to the earth, increasing the overall grounding effectiveness of the system. They also act as a backup, offering redundancy in case a water meter or building steel connections fail or become damaged. Ground rods provide protection against lightning strikes, helping to dissipate lightning energy, reducing the risk of damage to electrical equipment and the building structure. In some jurisdictions, ground rods are required by electrical codes to ensure proper grounding. When considering ground rods, soil conditions are an important factor. Ground rods are most effective in soils with low resistivity. If the soil resistivity is high, additional ground rods or other grounding methods may be necessary. Spacing and depth are important. Ground rods should be spaced and driven deep enough to achieve an optimal grounding resistance. Corrosion can be a problem. Ground rods can be prone to corrosion over time, especially in acidic or high moisture environments. Using corrosion-resistant materials or applying corrosion protection is essential. Cost is also a consideration. Installing ground rods can be more expensive than simply bonding to existing structures. Most experts recommend installing ground rods in addition to bonding the water meter and building steel. This provides the most comprehensive and reliable grounding system, ensuring the safety of electrical equipment and personnel. However, the specific requirements may vary depending on the soil conditions, building characteristics, and local code requirements. Consult with a qualified electrician to determine if ground rods are necessary for a specific situation. If ground rods are required, install them according to code specifications and ensure they are adequately spaced and driven deep enough. Periodically inspect and maintain the ground rods to ensure they remain effective and free from corrosion. Grounding electrode systems are vital for electrical safety. They provide a low impedance path for fault current to return to the source, allowing overcurrent protected devices like circuit breakers and fuses to operate and clear the fault. Without an effective grounding system, fault currents can take unintended paths, potentially energizing metal parts of equipment and creating a shock hazard. Grounding electrode systems typically consist of a combination of interconnected grounding electrodes such as ground rods, metal water pipes, building steel, and ground rings. The National Electrical Code, or NEC, provides detailed requirements for the design and installation of grounding electrode systems. Section 250.50 requires all grounding electrodes that are present at each building or structure to be bonded together to form the grounding electrode system. The intent is to create a single low-impedance ground reference point for the electrical system. Ground rods, typically 8 feet in length, are driven into the earth to provide a direct connection to ground. The NEC in section 250.52 specifies the requirements for ground rods. They must be at least 8 feet long and made of approved materials such as copper or galvanized steel. 2 or more ground rods are often required to achieve the desired grounding resistance. The NEC mandates in section 250.53 that if 2 or more ground rods are installed, they should be spaced at least 6 feet apart. This spacing helps to reduce the overlap of their effective grounding zones and improves overall grounding effectiveness. Metal water pipes, if in direct contact with the earth for at least 10 feet, can also be used as grounding electrodes. The water pipe must be electrically continuous and connected to the grounding electrode conductor. However, because water pipes can be subject to replacement with non-conductive materials such as PVC, they cannot be the sole grounding electrode. They must be supplemented by another type of electrode, such as a ground rod. Building steel, if effectively grounded, can also serve as a grounding electrode. The steel structure must be permanently connected to the earth through a grounding electrode conductor. A concrete encased electrode, also known as a U for ground, is another type of grounding electrode. It consists of at least 20 feet of bare copper conductor encased in concrete. This type of electrode is typically installed during the construction of a building. The grounding electrode conductor connects the grounding electrode system to the equipment grounding system and the neutral conductor at the service entrance. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The equipment grounding system provides a low impedance path for fault current to return to the source from electrical equipment. It consists of equipment grounding conductors run with the circuit conductors to each piece of equipment. These conductors are connected to the metal enclosures of equipment, providing a path for fault current to flow back to the source in the event of a ground fault. Ground fault circuit interrupters, or GFCIs, are devices that protect against electrical shock by detecting ground faults. They are required in many locations, such as bathrooms, kitchens, and outdoor areas. GFCIs work by monitoring the current flowing in the circuit. If a ground fault occurs, the GFCI will trip, interrupting the circuit and preventing electrical shock. Surge protective devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. SPD divert the surge current to ground, protecting the equipment from damage. Regular inspection and testing of the grounding electrode system is essential to ensure its effectiveness. Ground resistance testing can be performed to measure the resistance of the grounding electrode system to earth. A low resistance reading indicates a good connection to ground. The NEC requires that the resistance of the grounding electrode system not exceed 25 ohms. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. Proper installation and maintenance of the grounding electrode system are critical for electrical safety. Consult with a qualified electrician to ensure that the grounding system meets all applicable codes and standards. A well-designed and maintained grounding system protects people and equipment from electrical hazards. Bonding is another critical aspect of electrical safety closely related to grounding. Bonding ensures that all metal parts of an electrical system are at the same electrical potential. This minimizes the risk of electric shock by preventing voltage differences between conductive surfaces. The NEC defines bonding as the permanent joining of metallic parts to form an electrically conductive path that will ensure electrical continuity and the capacity to conduct safely any fault current likely to be imposed. There are two main types of bonding: equipment bonding and main bonding. Equipment bonding connects the non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and boxes, to the grounding system. This provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices to operate. Main bonding connects the service equipment enclosure to the grounded conductor, typically the neutral, at the service entrance. This establishes the connection between the grounding electrode system and the electrical system. The main bonding jumper is the connection between the equipment grounding conductor and the grounded conductor, the service equipment. The size of the main bonding jumper is determined by the size of the service engine's conductors, as specified in NEC Table 250.28. Bonding conductors are used to connect metal parts together. They must be sized according to NEC Table 250.102, based on the size of the circuit conductors. Bonding methods include using bonding bushings, bonding jumpers, and bonding lock nuts. Bonding bushings are used to bond metal conduit to enclosures. They provide a secure connection and ensure electrical continuity. Bonding jumpers are used to bond metal parts that are not directly connected. They are typically made of copper or aluminum and are sized according to the applicable code requirements. Bonding lock nuts are used to bond metal conduit to boxes. They are installed on both sides of the box and tightened to ensure a secure connection. The NEC requires that all metal parts of an electrical system be bonded together, including metal water pipes, gas pipes, and structural steel. This helps to minimize the risk of electric shock by preventing voltage differences between these conductive surfaces. In addition to the general bonding requirements, there are also specific bonding requirements for certain types of equipment and systems. For example, swimming pools, spas, and hot tubs have specific bonding requirements to protect against electric shock hazards. These requirements include bonding all metal parts of the pool, spa, or hot tub together, as well as bonding the equipment grounding conductors to the metal parts. The NEC also has specific bonding requirements for sensitive electronic equipment, such as computers and medical equipment. These requirements are designed to minimize the risk of electrical noise and interference. Proper bonding is essential for electrical safety. It helps to protect people from electric shock and to prevent damage to equipment. Consult with a qualified electrician to ensure that the bonding system meets all applicable codes and standards. A well-designed and maintained bonding system is a critical part of a safe electrical system. Grounding and bonding work together to provide a safe electrical system. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts are at the same electrical potential. Together, these two concepts help to protect people from electric shock and to prevent damage to equipment. The NEC provides detailed requirements for both grounding and bonding. It is important to understand these requirements and to follow them carefully when installing or maintaining an electrical system. The purpose of a grounding system is to provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. This helps to prevent electrical shock and to minimize damage to equipment. The purpose of a bonding system is to ensure that all metal parts of an electrical system are at the same electrical potential. This minimizes the risk of electric shock by preventing voltage differences between conductive surfaces. Grounding and bonding are essential for electrical safety. They help to protect people from electric shock and to prevent damage to equipment. Consult with a qualified electrician to ensure that the grounding and bonding systems meet all applicable codes and standards. A well-designed and maintained grounding and bonding system is a critical part of a safe electrical system. Ground resistance testing is an important part of maintaining a grounding system. Ground resistance testing measures the resistance of the grounding electrode system to earth. A low resistance reading indicates a good connection to ground, while a high resistance reading indicates a poor connection to ground. The NEC requires that the resistance of the grounding electrode system not exceed 25 ohms. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. There are several methods for performing ground resistance testing, including the fall-off potential method, the clamp-on method, and the slope method. The fall-off potential method is the most common method. It involves driving two auxiliary ground rods into the earth and measuring the voltage drop between the grounding electrode and the auxiliary ground rods. The clamp-on method is a non-intrusive method that can be used to measure the ground resistance without disconnecting the grounding electrode. The slope method is a more advanced method that can be used to determine the optimal location for additional grounding electrodes. Ground resistance testing should be performed regularly, typically every 1 to 3 years. The frequency of testing may need to be increased in areas with corrosive soils or high lightning activity. The results of ground resistance testing should be documented and kept on file. If the ground resistance is found to be too high, corrective action should be taken to improve the grounding system. Corrective actions may include adding additional grounding electrodes, improving the connections to the grounding electrodes, or replacing corroded grounding electrodes. Regular ground resistance testing is essential for maintaining a safe and effective grounding system. Consult with a qualified electrician to perform ground resistance testing and to recommend corrective actions if necessary. A well-maintained grounding system protects people and equipment from electrical hazards. Consider the use of exothermic welding, also known as a CAD weld, for creating permanent, reliable connections in grounding and bonding systems. Exothermic welding involves a chemical reaction that creates a molten weld, fusing the conductors together at a molecular level. This process results in a connection that is highly resistant to corrosion, vibration, and loosening over time, making it ideal for critical grounding and bonding applications. Unlike mechanical connections, such as clamps or lugs, exothermic welds do not rely on pressure or friction to maintain electrical continuity. This eliminates the risk of the connection degrading over time due to corrosion or loosening. Exothermic welds also have a very low resistance, providing an excellent path for fault current to flow back to the source. Exothermic welding is commonly used to connect ground rods to grounding conductors, bond metal pipes and structures, and create grounding grids. The process involves placing the conductors in a mold, igniting the exothermic welding compound, and allowing the molten weld to solidify. The result is a strong, permanent connection that will provide reliable grounding and bonding for many years. While exothermic welding requires specialized equipment and training, the benefits of using this method for critical grounding and bonding applications are significant. The increased reliability and longevity of exothermic welds can reduce maintenance costs and improve the overall safety of the electrical system. When designing and installing grounding and bonding systems, consider the specific requirements of the application and the environment in which the system will be installed. In harsh environments, such as those with corrosive soils or high humidity, the use of corrosion-resistant materials and methods is essential. In critical applications, such as hospitals and data centers, redundant grounding and bonding systems may be necessary to ensure uninterrupted power and safety. Consult with a qualified electrical engineer or electrician to design and install a grounding and bonding system that meets the specific needs of the application. A well-designed and installed grounding and bonding system is a critical investment in electrical safety and reliability. Remember to always energize electrical circuits before working on them. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable codes and standards. Electrical work can be dangerous, so it is important to take precautions to protect yourself and others. If you are not qualified to perform electrical work, hire a licensed electrician. A licensed electrician has the training and experience to safely and effectively install and maintain electrical systems. Working with electricity can be dangerous, but by following safety precautions and hiring a qualified electrician, you can minimize the risk. Ensure all electrical work adheres to National Fire Protection Association 70 or NFPA 70, otherwise known as the National Electrical Code or NEC. Understanding and following the NEC guidelines is paramount for ensuring electrical safety. Always consult with a qualified and licensed electrician for any electrical installations or modifications. Their expertise ensures compliance with local codes and standards, guaranteeing a safe and reliable electrical system. Remember, prioritizing safety and adhering to established guidelines are crucial when dealing with electricity.